Today, what we're going to talk about? We're going to talk about intermolecular forces, also known as IMF. Sounds a little bit cooler. Intermolecular forces. Okay, I have a water bottle right here. I have a question for you. How many water molecules do you think there are in this bottle? Guess. You can shout your answer, even though I can't hear you. 50, 100, 200. How many water molecules do you think are in this bottle? Millions. There are millions of water molecules in this bottle. Now, how come we have millions and millions of water molecules in this bottle, but they're not running away from each other? What holds them together? All these water molecules, they're nicely held together. What makes them to be held together nicely and they don't run away so I can have a water bottle? Intermolecular forces. So what IMF is attraction that keeps liquid and solid together. So it's attraction between the molecules that keeps the liquid and solid together. So my water molecules are held together nicely. Okay. Now let's look over here. So here I have a bunch of water liquid. I have a bunch of water liquid. This is my H2O liquid. And they are nicely held together through intermolecular forces. Now, if I heat up water, what happens? You already know that. If you heat up water, what happens? It goes into the gas phase, right? It becomes water gas. Now, when you heat up water and it becomes water gas, what are you doing? What are you doing? What makes it to go to the gas phase? You are breaking the intermolecular forces. You are breaking the intermolecular forces. You're not breaking any bond. The H2O bonds are pretty intact. The oxygen covalently bonded to hydrogen. You are not making those you're not breaking these covalent bonds. Those are much harder to break. When you heat up water, what you do, you're breaking the intermolecular forces, the attraction that holds the water molecule together. That's what you're breaking. And that's why water liquid goes to water gas. So far, so good? Okay. So it's the attraction that holds the liquid and gases together. So we need to learn about this IMF and to see what they are. And IMF is one of those topics that keeps coming back even when you go to organic chemistry. Okay, so we said again, when you heat up water, you are not breaking any bonds. You're not breaking any bonds. The only thing that you're breaking is the attraction between the water molecule. Now, we're going to go over the type of IMF you have. I'm going to list the IMF that we have. I'm going to list them from the highest to the low, the strongest to the weakest. The strongest IMF that I can have is ionic attraction. Then is hydrogen bonding. So I'm listing them from the strongest to the weakest IMF. So ionic, then the hydrogen bonding. Then the next one is dipole. And the weakest one that I have is London dispersion. So ionic, hydrogen bonding, dipole, and London dispersion. Now the question is, why do we care about this? Why do we care about these intermolecular forces? Why do we care about it? Okay. Now let me give you an example to show you why we care about intermolecular forces before I go over each one and see what each one is. So why do we care about it? Here's why you care about it. Let's say I have H2O, CHCl3, and NaCl. The boiling point for water is 100 degrees Celsius. For CHCl3 is 61.2 degrees Celsius. For NaCl is 1413 degrees Celsius. Okay. So here's why I care about intermolecular forces. Because if I know intermolecular forces, I can predict physical properties. I can predict physical properties. Because boiling point, freezing point, melting point, those all depend on intermolecular forces, right? For example, let's come over here. NaCl has ionic IMF. That's the strongest IMF you can have. So it's really, really hard to break those interactions. Hence, it has a really high boiling point. Water has hydrogen bonding. Still pretty strong IMF. It has 100 degrees boiling point, so I have to put in energy to do it. But it has a lower boiling point than NaCl because NaCl has a higher IMF, intermolecular forces. So we care about intermolecular forces because by knowing intermolecular forces, we can predict and determine physical property, and that matters. Okay, so far so good. Now that you know why we have to care about this IMF, we're gonna go one by one over each one to look at what they are. So the first one is ionic. So the first one is ionic. Now, ionic intermolecular forces is for ionic compounds. It's for ionic compounds. You know when we have ionic compounds. When we have ionic compounds is when we have plus minus attraction, right? So when you have ionic compounds, the interaction between those molecules are ionic intermolecular forces. So remember, ionic compounds is a plus minus attraction, right? It's attraction and plus minus attraction. Let's see, I have a bag of salt, okay? If I have a bag of salt is NaCl. How many NaCl do I actually have in that bag? Many, right? If I have a bag of salt, I don't only have 1 or 2 NaCl, I have a bunch of NaCl molecules that are held together through IMF. So I have millions of NaCl molecules that are held together through ionic attraction. Again, ionic attraction is basically a plus minus attraction. It's a plus minus attraction. So if I have NaCl, I have a bunch of NaCl together. They're held together through ionic attraction. They're held together through ionic attraction. I have this minus plus going on, and they're very nicely stacked up together through ionic attraction. Okay, so ionic, again, you know, every time you have a ionic compound is a balance of charges, plus minus charges. Those are held together through ionic attraction. And ionic attraction is the strongest attraction we have because it's the attraction between plus and minus charges. So they're pretty held together tightly. All right, so that's my ionic. So far, so good. Now, look at your list. What's the next one after ionic? So ionic for ionic molecules. What is the next one? Tell me. The next one is hydrogen bonding. The next one is hydrogen bonding. The next one is hydrogen bonding. Okay. Now, I always joke around that if you're taking a chemistry class, taking a chemistry test, and you don't know the answer to a question, and hydrogen bonding is one of the options, pick that option, and that's probably going to be right. But don't do that. Actually read the question and know the answer. Hydrogen bonding. What makes you you? What makes you unique? What do you think? My biologist. What makes you you? What makes you to be a unique human being? Your DNA, right? DNA, it makes you unique. It makes you to be you. Now, DNA is double helix, right? Everyone knows that? Yes. Especially my biology people. DNA is double helix. This is my double helix DNA. What holds the two strands of DNA together? What do you think? What holds the two strands of DNA together? Hydrogen bonding. So hydrogen bonding is responsible for you being you. I wasn't kidding about hydrogen bonding is pretty much responsible for everything, right? So DNA, two-stranded, held together through hydrogen bonding. Okay. Titanic. You guys have watched the Titanic movie? It's a little bit older movie for you guys now. Titanic happened because of hydrogen bonding. No kidding. Now, why did Titanic happen? Because they crashed into an iceberg. Have you ever thought about why ice is less dense than water liquid? Because usually in a liquid form, things are less dense, and in a solid form, the solid would be more dense. But not ice. Ice is less dense than water liquid. Why is that? It has to do with hydrogen bonding. And we'll go over what all this hydrogen bonding is, but I wanted to give you an overview of what hydrogen bonding plays a really important role in our lives. I wanted you to know that. So let's go over what is this hydrogen bonding that we keep talking about. Okay, let's say I have this and I have H attached to Y. Okay, now X and Y is oxygen, nitrogen, or fluorine. So far so good. Now pay attention to over here. Let's talk about this. So I have X, which is either nitrogen, oxygen, or fluorine. And what it has lone pair. So it has extra electron. It has lone pair, it has extra electron. It has extra electron to donate. Now I have hydrogen attached to Y. Okay. Now why I said is either nitrogen, oxygen, or fluorine. What can you tell me about oxygen, nitrogen, or fluorine? They are electronegative atom. They have a high En value. So this Y has a high En value. Now if I have a high electronegativity value, what that means is I'm pulling the electron towards myself, right? So if I'm pulling the electrons toward myself, that means this Y over here has more electrons than this hydrogen over here, because it's pulling the electrons this way. So I'm going to give it a partial negative and a partial positive over here, because it's pulling the electrons this way, so the Y has a little bit more electrons. It's not shared equally, right? It's a polar bond. That was our last chapter. So because this Y is pulling the electrons this way, that means this hydrogen has a partial positive, is desperate for electron. It wants electron. And guess what? This guy over here has electron to donate. Wants electron, needs electron, has electrons to donate, and hence they are going to interact, and that is my H bond. That's my hydrogen bond. To be cool, we can call H bond a hydrogen bond. So it's technically not a bond. Even if they call it H bond, it's technically not a bond. What is it? It's an attraction. It's an intermolecular attraction. It's an attraction, technically not a bond. It's an attraction. So far so good. Now, to have hydrogen bonding, what you need is HO, HN, and HF. You have to have the F and the N or the O be directly attached to hydrogen. If you don't have that, you cannot have hydrogen bonding. All right, so far so good. Okay. Now let's talk about why water solid is less dense than water liquid, because that really matters. Are you good with this one? Okay. So this is what hydrogen bonding is. You have HN, HO, or HF. Now I'm going to take a minute and I'm going to draw this out on the board. So bear with me for 1 second. Bear with me for 1 second. going to draw this out on the board, and then you please bear with me for 1 second as I'm drawing this out. I'm going to make sure I get this right. Perfect. So what am I drawing here? What I'm drawing here, I'm drawing a bunch of water molecules that are attracted together through intermolecular forces, through IMF, through hydrogen bonding, okay? And I can keep going, but I'm gonna stop here. Okay. I think that would hopefully show you what I mean. And I can draw a couple more to make sure that you guys are getting this down. There we go. Okay, now let's talk about this. Again, this is not the best drawing on the board, but if you even Google, and I can send you an image of it too. If you Google about a hydrogen bonding in water, you get a nicer drawing than this. So here's the thing. Water molecule, if I have a bunch of water molecules, like I said here, I have millions of water molecules in this water bottle. They're held together through intermolecular forces. The intermolecular forces that hold these water molecules together are hydrogen bonding for water. Now again, we said hydrogen bonding is when you have HO, HN, or HF to attach together. And here I have OH, right? I have oxygen attached to hydrogen. Oxygen is electronegative, so pulls an electron toward itself. This hydrogen is desperate for electron. Well, guess what? This oxygen has lone pair to give it to hydrogen, so they have a nice attraction going on. Okay, now here is a bunch of water molecules are attracted together through hydrogen bonding. When you look at that, what do you see? You see pockets. You guys see that? So when water molecules forms really nice hydrogen bond together, what happens is there are all these pockets that you see, all these empty pockets that you see, all these empty spaces that we have. When you have ice, solid, you have less movement in a solid, right? So when you have in a solid form, you don't have as much movement. Now, when you have less movement, you have all this beautiful hydrogen bonding that leave all these empty spaces, all these pockets. So that's where ice is less dense. Now, when you are water liquid, now there is more movement. There are more movement, so you don't have as many of these nice pockets. So they're more dense because you have more of the movement, so you don't have all these empty spaces. So you have all these empty spaces when you have a liquid, and that's why liquid has actually a higher density. So far, so good? Okay, so again, this is why ice is always less dense than water liquid. So far, so good? Okay, now I'm going to give you a practice problem to do. You ready? Let's do a practice problem with hydrogen bonding to make sure you really understand hydrogen bonding. I have an ammonia, I have two ammonia molecules. Can they hydrogen bond? Can they H bond? I have ammonia molecules. Can they H bond? Then what I have a CH4 and H2O. Can they H bond? Okay, you can pause my video, do this problem, and then unpause me, and then see what the answer is. So, I have two ammonia together. Now, you have to draw the loose structure. So this is good. This is a good practice for the last chapter. I have nitrogen bonded to hydrogen, and I have a lone pair on nitrogen. Okay? So far, so good. Now, I'm going to have another nitrogen. I'm actually going to draw with three oxygen attached to it. This is the Lewis structure for ammonia. Now, you see what's going on? This hydrogen is electron deficient. Because this nitrogen is more electronegative, is pulling the electron this way. And this nitrogen has a lone pair. So they could do hydrogen bonding. So the answer is yes, they could do hydrogen bonding. If I have another NH3 here, that N could be bonded to this hydrogen, and another NH3 here, the N could be bonded to that hydrogen. So yes, the answer is yes. Ammonia does a bunch of hydrogen bonding together. Now the other question is, can water and CH4 do that? Now let's draw CH4, and hopefully you're pretty good at drawing Lewis structure. Here's CH4, and here is water molecule, okay? Here's CH4 and here's a water molecule. Now remember, to do hydrogen bonding, you need NH, OH, or FH, right? So water has OH, that's perfect. Water can do hydrogen bonding. But can CH4 do hydrogen bonding? CH4 cannot do hydrogen bonding. And here's why. Carbon is not that electronegative. So this hydrogen is happy. This hydrogen is actually pretty happy. It has some electron. It doesn't have his eye on that oxygen lone pair. It's pretty happy. So no, it's not going to hydrogen bond. To a hydrogen bond, you need NH, OH, or FH. You need to have those to hydrogen bond. So far, so good. Okay. So what was that? That was our hydrogen bonding. Now, what is the next one? What is the next one? I want you to look at the list that I gave you at the beginning of class. The next one is dipole-dipole. The next one is dipole-dipole. The next one is dipole-dipole. Now, you do dipole-dipole. So we said ionic is attraction for ionic molecules. And we said hydrogen bonding is when you have NH, FH, or OH. Dipole-dipole is when you have covalent compounds that are polar. Covalent compounds that are polar, that becomes dipole-dipole. Let's do an example. Let's do H2 HCl molecules next to each other. Hydrogen versus Cl. Which one is more electronegative? Cl. Good job. So what does that mean? Cl is more electronegative. It's going to pull the electron toward itself, so it gets a partial negative, and the hydrogen gets a partial positive because hydrogen doesn't have enough electron and Cl has too much electron. Do you agree? Okay. So if I have a hydrochloric acid bottle, which means I have a bunch of HCl molecules in there, right? So if I have a bunch of HCl molecules in there, how are they held together? You can probably tell me by looking at this. You see what the attraction is going to become? This Cl has a lot of electron, this hydrogen doesn't have a lot of electron. So where is the attraction going to come? The attraction is going to be right here. The attraction is going to be right here. So far so good. That's where the attraction is going to be. This is my attraction. And remember, HCl is polar, right? HCl is polar. That's where the attraction is going to be. So far so good? Okay. Now, let's do a practice problem. You ready? Here's our problem. Boron difluoride. Okay. What type of IMF.BF3 has? Now, the first thing that we need to do, we need to draw it out. Here's boron. Here's fluorine, fluorine, fluorine all around it. Okay? You guys agree with that? Because remember, boron is one of the exceptions. Boron is happy with 6 valence electron. All right. Is this ionic? It's not ionic because this is not an ionic compound. Is it hydrogen bonding? It's not hydrogen bonding because you don't have OH, NH, or FH. Is it dipole-dipole? Well, it's covalent, but is BF3 polar or non-polar? BF3 is non-polar, right? Because remember, all the dipoles are going to cancel out. Electrons are distributed evenly around the molecule. It's trigonal planar. That's a non-polar geometry. Okay? So it's not ionic because it's not an ionic compound. It's not hydrogen bonding. I don't have NH, FH, or OH attached together. It's not dipole-dipole because dipole-dipole is for covalent that are polar. That's why we have this attraction when they're polar. So it has to be London dispersion. So let's go over what is London dispersion. Let's go over what is London dispersion. Now, London dispersion is for, like BF3, covalent and non-polar. So it's for when you have covalent that is non-polar. It's for covalent that is non-polar. Okay? So let me draw the BF3 again. Covalent that is one second to do this right. Covalent that is non-polar. And now let's go over this. Let's go over this to see what's going on here. So remember how we said if we have this, so here's my boron in the middle, and F and F and F is over here. Okay. Now if you look at this, electrons are distributed evenly around the molecule. That's what makes it to be non-polar. Okay. Now here's the thing. There is a constant motion at room temperature. There is a constant motion at room temperature. These are moving rapidly at room temperature. Now, because they're moving rapidly at room temperature, sometimes they end up having a temporary dipole. What does that mean? So, there's a constant motion. They are moving rapidly at room temperature, right? They're moving rapidly at room temperature. Now, because of this constant motion, they're moving randomly at room temperature. Once in a while, they create a temporary dipole. Once in a while, they create this temporary dipole. Now I have a partial negative, partial positive, partial negative, partial positive, and bam, there's an attraction over there. Now, they call it induced dipole. It's only temporary. It's only temporary. Again, they're moving, there's a constant motion at room temperature, and sometimes they develop this induced dipole, this temporary dipole. And that's why London dispersion is the weakest one, right? Because it's induced dipole and it's only temporary. Now, as they're moving around, you're going to get into orientation that is not distributed evenly around the molecule. So what you have a temporary dipole. Are we good so far? Okay. Now I'm going to repeat this one more time to make sure you really understand this. So electrons are constantly moving. They're constantly moving, orbiting around the nucleus. Now by chance, temporarily, they sometimes gather on one side of the molecule. And then when that happens, you end up having induced dipole. So by chance, they end up gathering on one side of the molecule, and what you're doing, you're creating a temporary dipole. So far, so good? Okay. Now, let's do another practice problem. So again, this is an induced dipole as the electrons are moving constantly around the nucleus. Once in a while, by chance, temporarily, they might gather on one side of the molecule, and then they come to close proximity and they have this induced dipole. Here's an example on what I need to do. Cl2 versus H2. Which one has a higher IMF? Which one has a higher IMF? What do you think? Which one has a higher IMF? So, Cl2, is it ionic? No. Hydrogen bonding? No. You have to go one by one on the list. Two nonmetals together, okay? So it's covalent. That's good. Now, is it polar or non-polar? Cl2 is non-polar. So that would be, it would have London dispersion. We also write it as LD. How about H2? The same thing. It's going to have London dispersion. So they both have London dispersion. So now if you have two molecules that they both have London dispersion, which one is going to have a higher IMF? What do you think? Okay, so if you have two that they both have London dispersion, the larger atom, the one with more electron, is going to have a higher IMF. So here's what, and I'm not talking about valence electron, total electrons. Because the more electrons that you have, what does that mean? The more higher chances that you have that you can form this temporary dipole. Also, if you have a larger atom that has a lot of electrons, that means some of the electrons are far away from the nucleus, right? You have electrons that are far away from the nucleus and is less tightly held together. Hey, they more easily can form this temporary dipole. We talked about it. Here's the nucleus being the mom, electrons being the kid. They're far away from the nucleus because you're a large atom. If you're a large atom, some of your electrons are far away from the nucleus. They're not feeling the plus charge as much anymore. Hey, probably more easily they can form that temporary dipole. So the larger atom has a tendency to have a higher IMF. So the answer would be Cl would have a higher intermolecular forces. Okay, we're good so far. Nice job. Now, ready to do a practice problem? Okay. Now, I'm actually going to give you a take-home problem for practice. And then next video, we're going to talk about this. Here's a practice problem. HF, H2, Cl2, calcium chloride, CH3Cl. What I want you to do, I want you to rank from highest to lowest IMF. Rank it from the highest to lowest IMF. Now here's a hint. You know what we talked about. Go for each one, go on the list. Is it ionic? Is it hydrogen bonding? Is it covalent? If it's covalent, then is it polar or is it non-polar? To figure out what kind of IMF it has. And for covalent one, and even for hydrogen bonding, sometimes you have to draw it out. Do the Lewis structure in order to be able to do this. Okay, so this is your take-home problem. You're not really taking it home, you're already home. We'll do this next time. Nice job today.